quadrature amplitude modulation, which is a form of digital modulation that combines the ideas of PSK and ASK. And with QAM, the amplitude is used to modulate the carrier signal, or rather, the binary data stream is used to modulate the amplitude of the carrier. But the carrier is divided, has two components, while one is 90 degrees out of phase of the other. So we will have cosine carrier and sine carrier, and we are going to be separating the binary data stream using the serial to parallel, serial to parallel converter. So we may opt to have the even and odd bits separated, and therefore the even bits combines with the sine carrier, and the odd is used to modulate the cosine carrier. So the amplitude is the one that is the amplitude of the sine carrier is the one that carries the information that is carried by the bit. So for that reason, we are going to be having two carriers, and the two carriers are 90 degrees out of phase, but the message signal is carried using the amplitude of that carrier. So that way we are able to achieve modulation by combining the phase and the amplitude of the carrier. So for a modulator, which is rather simple, we say that two different signals are sent simultaneously by using identical copies of the carrier. So the two carrier signals are identical in frequency, but one is 90 degrees out of phase from the other. So in figure 932, we are able to see that sample modulator, in which we have the input binary stream, and then the binary data is arriving at a rate of SB bits per second. And at this stage, or this block diagram, we are able to generate two streams of data by taking the alternate bits, similar to what we did with the QPSK. So we may take even going that direction and the odd bits going that direction, or vice versa. So we can actually say this is odd, this is even. So one data stream is ASK modulated on a carrier FC, and the other is also ASK modulated by the same carrier, but the major difference occurs here, where this carrier that was cos is shifted to become pi, and therefore we are talking about ASK modulation. So it is like combination of ASK and PSK, but in this case, once we have shifted the signal of the two carriers by 90 degrees, we do not modulate the phase anymore. Rather, we will be now modulating the amplitude. So we say that the two modulated signals are added together and transmitted. So when you add the two modulated carriers, you get your QEM signal. So this question 932 is the way you would express your QEM mathematically. So the major difference between PSK and ASK is that here we have the phase that remains at 90 degrees out of phase, but the amplitude is changed by the binary data stream that you are transmitting. Now talking about the demodulator, we will borrow the ideas that we have seen with the QPSK, where we are using the mth power to recover the coherent carrier at the demodulator. So we are splitting our QM signal into three. One of them is sent to correlator 1, the other one is sent to correlator 2, and the other one is sent to this carrier recovery circuit. The purpose of this is to just get our recovery circuit, get our recovery carrier signal. When we pass it through a narrow band pass filter centered at 4 FC, and you divide that output by 4, we are able to get our carrier signal or coherently, and then this carrier signal is the one that we are using to multiply with the balance modulator from the QM signal that we have received, and we do the same thing that we did earlier. Cos A cos B is equivalent to 1 over 2, or rather this cos equals A. 1 over 2, 1 plus cos 2A. And for that reason, this becomes high frequency component that is cut off by the integrator, and we are left with the signal that we are able now to convert using analog digital converter, and which we are able to get digital pulses, because now this, remember that the signal was carried by the amplitude. So when you use the AD, we are able to get two possible values, a high or a low, and that high is now going to be used to as the input to our parallel to serial converter that now generates a series or a sequence of zeros and ones. So a high is going to be represented as by a 1, and a low is represented by a 0. For that reason, we are able to get that, and that becomes rather straightforward. So we say that QAM, coherent demodulator, is similar to that of MRA-PSK, coherent demodulator, except that we have M is equals to 4. In MRA, we could have M equals to 8, among others. So a local set of quadrature carrier signals is recovered for synchronous detection by raising the received signal to the code power. We have seen that in this section. And then the component of FC is extracted using the narrow bandpass filter that is tuned at 4 FC, and then divided by 4 to get our coherent carrier signal. And therefore the available quadrature carrier signals are applied to two correlators, each comprising of a balanced modulator and an integrator. And we have seen that the integration is done over time interval equal to the sample period, and therefore we are able to receive our analog signal that is taken through the analog to digital converter, which now gives us our binary data sequence. And now we talk about the bandwidth of QAM, rather straightforward, similar to what we did with MRA-PSK. We see that the bandwidth will be given by 2FM divided by log of 2 of M. So this is the number of symbols. In our case, our M is equals to 4. Therefore, we are seeing that this is log of 2 of 2 becomes log of 4 of 2 becomes 2, and therefore this 2 cancels out, and we are left with for 4 QAM, we are left with the bandwidth of FB. For 8 QAM, we say that it is 2 FB divided by 3, because log of 8 to base 2 is definitely equals to 3. And similarly for QM is equals to 16, we are able to find that this becomes 2 FB divided by 4 becomes 1 over 2 FB. So that is how you are able to evaluate the bandwidth of QM signal.